Hello students, in this lecture video I am going to solve two derivation, that is derivation for a shape function of a 1D heat conduction and stiffness matrix due to conduction. Okay, so these two derivations are required to solve numerical problems. Okay, so what I am going to derive the formula by in this two derivation, those two formulas are very important to solve numerical problems on, that is heat transfer. Okay, so let me start the first derivation, that is derive the shape function for one dimensional heat conduction. Okay, so in the introduction class I told about what you mean by conduction and convection and radiation. Okay, that is the heat transfer methods will be there. Okay, so now in this okay, so the first derivation is in this is all, these two derivations also very important for the examination. Okay, so derive the shape function of 1D heat conduction. Okay, so in the previous case I told many times the shape functions are denoted by capital N1, N2, N3, N4. Okay, so look at this. So in this we are going to derive the same what we derived in the previous model. So similarly we are going to derive the shape function for heat conduction. Okay, look at this. Consider a one dimensional bar element. So this is a one dimensional bar element having the two nodes, that is a node number 1 and node number 2. Let T1 and T2 be the nodal temperature. Okay, be the at node number 1 and 2. Okay, so T1 and 2 are considered as the degree of freedom. Okay, in the previous lecture video we are going to consider the V1 and theta 1 are the displacement. Okay, in the beam chapter. Okay, just to replace the V1 theta 1 to here at nodal temperature, that is T1 and T2. Okay, so consider this as a natural coordinate system. Okay, from this point. Okay, so from this point to this point. Okay, that is the x1, that is this is a global stiffness matrix. Okay, let us consider a global stiffness matrix, that is what global natural coordinate system. Okay, so consider this is a global natural coordinate system. Let us assume draw a line from, we are going to measuring from this, that is let us assume from this point to this point, this is the origin. Let us like a length, that is the distance x1, and from this point to at node number 2. Okay, so the length is x2. The difference between these two is nothing but x2 minus x1. This is the L. Okay, so node number 1 to 2, the distance is L is equal to x2 minus x1. Okay, T1 and T2 be the nodal temperature. Okay, so this is what the finite element model for the this 1D bar element. Okay, so let us assume, already we know this, let us assume the nodal temperature, that is it is similar to the interpolation model what we did in the previous case, that is the previous model. Okay, so let us assume the linear temperature distribution with the help of the polymer function. We have, this is a 1D bar element. We know that for the 1D bar element the polymer function or interpolation function which is given by, okay, T of number of element, that is T, E stands for x. Okay, T of x is equal to A0 plus A1 x. Okay, give equation number 1. Okay, so that is 6.48. Okay, so again we have if you write this in matrix form, okay, we are going to get like this: T of x is equal to 1 comma x, A0 A1. Okay, so where A0 A1 are the generalized coordinate system, okay, that you need to calculate by applying the boundary condition in the given diagram. Okay, so this is in matrix form. These both equations are same only. If you multiply this to this, you are going to get this only. Okay, how means 1 into A0 and this A1 x into A1 x. Okay, so this is in the matrix form you are going to write. Okay, so give equation number 6.49 this. Okay, so where A0 and A1 are the generalized coordinate system which we need to calculate by applying the boundary condition. Okay, so now look at this at node number 1. What are the boundary condition at node number 1? So x is equal to x1, t is equal to t1. Okay, so that x is equal to x1 at t is equal to t1 at node number 1. Okay, at node number 2, what is the boundary condition? X is equal to x2, t is equal to t2. Okay, so these are the boundary condition. Okay, so substitute x is equal to x1, t is equal to t1 in this equation. Okay, so you are going to get this, that is t1 is equal to a0 plus a1 x1. Okay, so give equation number, the next equation, that is 6.50. Okay, again by substituting this equation in the boundary condition in this equation. Okay, so in this equation you are going to get this t2 value. Okay, t2 is equal to a0 plus a1 x. Okay, now these two equation you have to write in the matrix form. Okay, so equation number this and this, if you write the in matrix form, so t1 t2, so here 1 x1 1 x1 x2, so these are the generalized coordinate system a0 a0. Okay, even if you multiply this you are going to get the same equation. Okay, so give equation number 6.52. Okay, so now again just to remodify this equation. Okay, so this you turn this side and this become this side and it will become transpose. Okay, just to remodify this, a0 a1 is equal to 1 by transpose equal to t1 by t2, that is t1 t2. Okay, give equation number this, give equation number 6.53. Okay, so now you take just to rearrange this. Okay, so that is 1 by x2 minus x1. Okay, so 1 minus x2 minus x2 minus x1, if you wrote this transpose, okay, it will become okay, so that is t1. Okay, so if you multiply these two you are going to get same value here. Okay, so that is just to modify this equation to like this: 1 by x2 minus x1, inside is x2 minus x1 1. Okay, if you multiply these two you are going to get same value. Okay, so now a0 a1 equal to, so a naught a1 which is equal to 1 by this x2 minus x1 nothing but what, length. Okay, look at here, x2 minus x1 nothing but what, the length will be there, x2 minus x1 is equal to L, so that you have to substitute in this. Okay, 1 by Le, so x2 minus x minus 1 1, okay, t1 t2. Okay, now where L is equal to x2 minus x1, it is the effective length of the given one dimensional heat conduction bar element. So where a0 and a1 with the generalized coordinate system. Okay, so again you have to modify this equation. Okay, so again you have to modify this, t of x is equal to 1 by Le, x2 minus x1, okay, minus 1 1 t1 t2. Okay, so just to modify this again, here you have to take 1 by Le, just modify this. Okay, x2 minus x1 minus 1 1 t1 t2, just to rearrange this to this. Okay, so now you have to multiply this to this. Okay, 1 by Le, 1 into x2 okay, 1 into minus x x into x2, that is here next one is x into this x minus x1. Okay, once you multiply the first row first column, second row second column, if you multiply this you are going to get this x2 minus x1 x minus x1, this is right as it is. Okay, so t of x is equal to, again you have to multiply this into inside. Okay, so inside you have to multiply. Okay, that is x2 minus x1 Le, x minus x1 Le, t1 t2 will be there. Okay, so give equation number 1. Okay, so this is, let us assume this equation is equal to n1 and this is equal to n2, so t1 t2. Okay, so now if you multiply this n1 t1 n2 t1. Okay, where n1 is equal to this x2 minus x L1. Okay, so where n1 is equal to x2 minus x1, I wrote here n1 is equal to x2 minus x1 and n2 is equal to this x minus x1 Le. Okay, so these are called as the shape function for one dimensional heat conduction. Okay, so these are the very very important while solving the problem. Okay, so that is these two, with the help of only these two elements we are going to derive the free convection. Okay, left hand free convection, one end is free, another end one is force is exposed to the environment, that okay, all of those equations we are going to derive with the help of this equation, you have to remember. Okay, the shape function are denoted by n1 and the heat conduction shape function is n1 n2, so that is which is given by x2 minus x1 Le. Okay, so these are the shape function for the one dimensional heat conduction, that is the first derivation. Okay, up to now, up to here we have to solve. Okay, so these are called as shape function. Okay, coming to the second derivation. Okay, derive the stiffness matrix or the conductivity matrix for the one dimensional heat conduction. Okay, so how we derive the stiffness matrix for the truss element, beam element, okay, so torsion element. Okay, like that you have to derive the stiffness matrix for this heat transfer due to conduction. Okay, so conductivity matrix due to conduction. Okay, convection is different. Okay, so conduction is different. Okay, so let us assume they consider a one dimensional bar element having two nodes, that is 1 and 2, t1 and t2 are the nodal temperature at node number 1 and 2. Okay, consider this diagram in a global coordinate system. Okay, so let us assume this is a reference point. From this point to this point, length is x1, and from this point to node number 2 is x2. This is the x2 minus x1 is equal to Le, so these are the t1 and t2. Okay, so we know that the stiffness matrix. Okay, the stiffness matrix for the element, that is k is equal to, we have the integration of 0 to L. Okay, strain displacement matrix, that is B transpose and D and B into dV. Okay, so where D is equal to strain displacement matrix. Okay, so where B is equal to what, so B is equal to strain displacement matrix, which is given by dn1 by dx and dn2 by dx for the with respect to the heat conduction. Okay, where D stands for the, which is equal to stiffness matrix for the one dimensional heat conduction. Okay, so where we know the n1 and n2 value already we derived in the previous equation, that is n1 is equal to x2 minus x, okay, Le, and n2 nothing but x minus x1 by Le. Okay, so strain displacement matrix we have. Okay, note down from this again, B is equal to, so substitute in this. Okay, that is minus 1 by Le, 1 by Le, and B transpose is equal to, note down here. Okay, so same one you have to transpose this. Okay, so consider equation number 1 6.60. Okay, so substitute the 6.0 in equation number 6.59. Okay, so in this. Okay, so wherever it is there, that shape function value substituted in this equation, so you are going to get this kc is equal to integration of 0 to L, so beam, so minus 1 B transpose is equal to minus 1 by Le, 1 by Le, so k is as it is. Okay, minus 1 by Le, minus 1 Le. Okay, so again here A and K are the constant term, so note down here, outside K is nothing but thermal conductivity and A stands for the area. So integration of this, so if you multiply this to this nothing but you are going to get 1 by Le square minus 1 by Le square minus 1 by Le square 1 by Le square. Okay, these are negative sign, these are positive signs. Okay, so that you have to remember into dx. Okay, so again integration of this dx. Okay, so AK as it is, this is also constant term, write down as it is, integration of 0 to L is equal to dx. Okay, so we have the integration of 1 nothing but we are going to integrate Le, so integration of of 0 to L nothing but Le. Okay, AK Le. So write down this as it is. Okay, now stiffness matrix for the heat conduction. Okay, now AK Le. So 1 by L square if you take common here. Okay, so that if you take here what 1 by L square if you take common means here Le get cancel AK L. Okay, so that is AK by La. So inside is 1 minus 1 minus 1 1. Okay, so this is stiffness matrix for the heat conduction is given by Kc is equal to AKL 1 minus 1 minus 1 1. Okay, so where A stands for the area of an element. So if in the composite wall if they not given in the problem means let us assume area is equal to 1 while solving the problem. Okay, K stands for the thermal conductivity, L stands for the length of the effective length. Okay, so unit also I mentioned here, area is equal to in meter square, K is equal to watt per meter Kelvin, and length is equal to in meter. Okay, so these unit you have to maintain while solving the problem. Okay, so this equation is called as element stiffness matrix for it is what stiffness matrix for one dimensional heat due to conduction. Okay, so these two derivations are very important, and these two formula I am going to use while solving the problem. Okay, so if in the given problem area is not given means let us assume area is equal to 1. Okay, so I hope you understand these two derivation. Okay, in the in the heat transfer model these two derivations are very important. Frequently they are asking to derive the shape function for heat transfer and derive the stiffness matrix for one dimensional heat transfer due to conduction. Okay, so you have to remember these two derivation, you have to practice more. Okay, so I hope you understand this. Okay, thank you.